Good evening. Are you able to hear me?
Yes.
Okay. So let us slowly start today's session. So let me share my screen first. Okay. So let's start today's session. So we will just start with what are all the concepts we have covered in the week 4. We will not go through all the details. Actually, week 4 is a uh, very basic session. Mainly, it was dealing with the determinants. So we will just go through the concept first, and later we will go to the problem. So in the first 10-20 minutes, we will just see what are all the things that covered in the week 4. So you might have already studied what is determinant and all the properties. So basically this determinant, adjoint, these are all the things covered in the last week. So I am not saying what is determinant or how to find the determinant, as you already know that. So let us see some basic properties of determinants first. Okay, so the first one is, if there are identical rows, if there are identical rows for a matrix A, then what will be the determinant of A? If two rows,
Zero.
yeah, determinant of A will be 0. The identical rows means the rank is less than n, where n is the order of A. So obviously, strictly less than n rank means determinant is 0, or actually this is the equivalent condition. Full rank, determinant is non-zero. Rank is strictly less than n, determinant is 0. Okay, so the second property is, okay, if a row is a linear combination of some vectors, then determinant is a linear combination of corresponding matrices. So if there is some row, it is a linear combination of some two vectors. If Ri equal to some C1 Rj plus C2 Rk, like this. So then we can split the matrix into two matrices with the C1 into the matrix which contains the Rj only. All other entries are same, all other rows are same, plus C2 into the matrix containing the in the ith position the row Rk, and all other rows are same. So we have two matrices. Find the determinant of these two matrices and take the linear combination. This will be the determinant of the original matrix. That is what it is saying. And the third property is, determinant of I equal to, what is determinant of the identity matrix?
1.
Yeah, determinant of the identity matrix is 1. So these are the basic three properties. And now, okay, I will go further. Now if B is a metric, B is obtained from A by interchanging two rows. Suppose I am interchanging first and second row. So what will be the determinant of A in terms of determinant of, determinant of B in terms of determinant of A?
Negative.
Yeah, if we are interchanging rows, then determinant of B will be negative of determinant of A. And if two rows are linearly dependent, what we can say determinant of that matrix? If two rows are linearly dependent, means one can be written in term of other, like as a constant multiple or linear combination.
Zero.
Two, yeah, two rows are linearly dependent, then determinant of A equal to 0. Okay, if A is invertible, uh, invertible, then what is determinant of A inverse?
1 upon determinant of A.
Yeah, 1 upon determinant of A. In case of A is not invertible, what is the determinant?
0.
Yeah, it is 0. Okay. That is why we are stating the condition A is invertible. If determinant of A is 0, 1 upon determinant of A is not valid, right? So, if A is invertible, then only A inverse exists, then only we can state this condition. Okay, if AB are two matrices, AB are n by n matrices, then what is determinant of AB?
Determinant of A into determinant of B.
Yeah, determinant of A into determinant of B. So these are the very basic things that we can use while doing the calculations. Okay, now one theorem we can state. So the following are equivalent for an n by n matrix A. So the first condition is A is invertible. A is invertible means by definition it has a some matrix B such that AB equal to BA equal to identity. So that is the definition of invertibility. Now an equivalent condition for invertibility is A has determinant non-zero. Okay, A is invertible and determinant is non-zero are equivalent. And A has full rank. That is, if A is an n by n matrix, rank of A is n. Okay, A has full rank. That is, rank A equal to n. Okay, so this theorem, this is a very basic result. So, but it is helpful while doing the problems. Now, one notice determinant of A equal to determinant of A transpose. We already know what is A transpose. It is the interchanging row and column. Okay. So then determinant of A and determinant of A transpose are same.
Ma'am, just sorry to interrupt you.
Yeah.
Uh, can you please also cover the block matrices, because in the assignment there is a question on block matrices, and I don't have much idea about how the operation work if there is a block matrix.
Okay, block matrix, what exactly block matrix says in operation, we cannot say how operation works. Like block matrix
Mhm.
itself is a matrix. So whatever the operation in the matrix, that satisfies for block matrix also. So when we say a block matrix, suppose usually we will write a matrix A, X, Y, Z, W. Actually, this is a block matrix means independently this X, this
Yeah.
y, this z, this w. Okay, all are matrices. Okay, now suppose X is an m by n matrix. Okay, for simplicity, I will start with some examples. Okay, suppose X is a 3 by 3 matrix. Okay, so what I am having is uh, X is a 3 by 3 matrix. Now, block matrix means we have 3 rows for X. Okay, Y is coming just near to X. So, Y should also have 3 rows. Okay,
Mm.
so Y has 3 rows, but number of columns, suppose it can 4 also. Okay, so the matrix will be like here 1, 2, 3, 3 rows and 3 columns here for X. Okay, and corresponding to Y, again we have 3 rows only. That means we are splitting along this way. Okay, 3 only, but columns we have 1, 2, 3, and 4. Okay, so X is one block, Y is another block, and Z. For Z, how many columns should be there?
Uh, 3.
Yeah, it should be 3 because it is just below 3, and after the third column we are splitting it. So 3 columns are there for Z. Okay, Z has 3 column, and its row can be any, maybe it can be 5 also, or it can be 2 also, anything.
Yeah.
Okay, so here also we have split along this one, and we have 2 rows, 1, 2, 3 columns. Okay, and in the same way, what should be the order of W then?
Same number of rows as Z
Yeah,
and same number of column as Y.
yeah, so it should be 2 by 4, correct?
Mm.
Okay, so this is how we are finding the block matrix. Okay,
Yeah.
in general, we cannot say like if we have some matrix A, B, C, D, what we will do, determinant means AD minus BC, correct?
Yeah.
So in general, we don't know
Can we say
determinant of A is determinant X, determinant
like
of W. That we
X,
cannot say.
XW
Okay,
is equal to ZY? We cannot.
no, no, we
There.
cannot say.
Okay.
Okay, there can be cases. So, in some cases it can be true, some cases it need not be true. For example, we can see.
If we
Uh,
take if all are same size, then can we say like all are same size matrix, like 3 by 3, 3 by 3, all are 3
hmm,
by 3.
hmm.
Can we say XW minus uh, ZY is the determinant of A?
I don't think we can say. Actually, that is the one question I think I should
Yeah,
not
that is.
answer.
Yeah.
Uh, I'm not supposed to answer, but still,
Okay.
uh, there are some conditions.
Yeah.
Like, okay, as I told, here we have 3 by 4, 2 by 4 matrices. There is nothing to be so called the determinant here.
Okay, fine.
But in the case of, in general case, okay, you have to find the counter example. First try with
I
some
just
small
took a
matrices, 2 by 2 matrix.
yeah,
Yeah.
I took a sample and then I tried, but it was not matching the what is given in the question. So I have put it as false. Uh,
See, if you are able to find such
yeah,
determinant of A equal to determinant of X, determinant of W minus determinant of Z,
yeah,
determinant of Y. If we are able to find at least one counter example such that it is false, then the result is false.
correct. Yeah,
Okay, if we
yeah,
are able to prove it in general for any matrix, like whatever the order n by n matrix, and whatever the matrix we are taking, then the result is true.
yeah.
So that is how we usually tell like whether it is true statement or wrong statement.
Okay.
Okay,
Yeah,
okay, yeah. So we will go to.
yeah,
So the remaining are minor cofactor and all. So minors and cofactors. So do you want me to revise this and adjoint? Do you want me to revise the definition?
Yes, Mrs.
Okay. So first of all, we will say what is minor. Okay, so what minor is, if we have some matrix, okay, suppose Aij is some element, some entry in the matrix. So we will delete the corresponding column and corresponding row of Aij. Like in which column it lies, we will delete that, and in which row it lies, we will delete that. So the remaining one, okay, A is a n by n matrix. So after deleting one row and one column, so the remaining one is a n minus 1 by n minus 1 matrix. Okay, so that value is the determinant of that value is the minor. Okay, so whatever we are getting the n minus 1 by n minus 1 matrix, we will find the determinant of the value, and that value is the minor of Aij. So Mij denotes the n minus 1 square matrix obtained by deleting ith row and jth column. So Aij means the element in the ith row, jth column. So deleting that ith row and jth column, the matrix we are obtaining, we will call it Mij, and determinant of Mij is the minor of Aij of A. Okay, minor of Aij of A, and cofactor. So cofactor means, so whatever we got, the Mij value, determinant of Mij value we are getting. So we will take the sign accordingly, like according to the position. Okay, minus 1 power I plus j. So for example, if it is A11 here, so what we will take, minus 1 power 1 plus 1, and determinant of this matrix. Okay, so this is the cofactor value corresponding to A11. Okay, so the matrix Aij is the cofactor matrix. Okay, take an element Aij, remove the corresponding row and column, find the determinant of the remaining n by n minus 1 by n minus 1 matrix, and multiply that value with minus 1 power I plus j, write it in the Aijth position. So the matrix obtained like that is the cofactor matrix. Now adjoint is nothing, just take the transpose of the cofactor. Transpose of the cofactor matrix. Okay, so these are all the things we have here. Now, okay, one important result is, if A is a square matrix, A into adjoint of A equal to adjoint of A into A equal to determinant of A into I. So this again we will use this result frequently in solving the problem. And A inverse equal to adjoint of A by determinant of A. So this is how we can find the value of A inverse if a matrix is given. Find the adjoint of A as earlier and divide each entry with the determinant of A. So whatever we are obtaining is A inverse. Now we have the concept of rank. So we already know what is rank. We have already seen what is rank, but using the determinants also we can redefine the rank. Okay, so if A is a square matrix, actually it is not needed a square matrix, like any matrix is fine. Then rank of A equal to maximum of R such that there exists a R by R submatrix with the non-zero determinant. Okay, so if we have a matrix, given any matrix, so if it is a square matrix, we will find out the determinant of that. If it is non-zero, then rank is the order of the square matrix. If it is 0, then we will see the n minus 1 by n minus 1 sub-square matrices and find the rank. Okay, so for example, why I am saying for non-square matrix also it is true. For example, suppose 2 3 4 1 2 3, something like this is there. Okay, so by definition only thing is the maximum value of R such that an R by R square matrix has non-zero determinant. Here we can take like for this matrix we cannot find determinant. Okay, it is not a square matrix, so determinant is not defined. But we can find the square matrix of order 2. For example, 2 3 1 2. Okay, its determinant is 4 minus 3 equal to 1 non-zero. So it has rank 2. Okay, rank equal to 2. Rank of the original matrix this. Okay, rank of this matrix is 2. Okay, so even though we don't have a square matrix, we can find the sub-square matrices. Using that, we can find the determinant. Now, let me give an example. For example, 1 2 3 1 2 4. So can anyone say what is the rank of this matrix? Using this determinant, like anyway you can do, but still using the definition we have now mentioned, can anyone say what is the rank? Is it 3?
No, 2.
Yeah, rank is not 3. Okay, because if we are taking the, suppose this is A, clearly determinant of A equal to 0. Okay, because the first row and the third row are same. Okay, then determinant will be 0. We already told if we have same equal rows, then the determinant will be 0. So for any 3 by 3 matrix, like any 3 by 3 matrix formed from this, we have the rank is a 0 value. Now if we are considering 2 by 2 matrices, first one we will consider 1 2 1 2. Okay, 1 2 1 2, its determinant is also equal to 0. See, I am taking this submatrix 1 2 1 2. It has also determinant 0, but still we cannot say uh, it has rank 1. Okay, because we need to consider all 2 by 2 matrices. For example, we need to consider this also. Now I am considering this submatrix. So what I will get? 2 3 2 4. So it has determinant 8 minus 6 equal to 2, which is non-zero. So I got at least one matrix of order 2 with non-zero rank. sorry, non-zero determinant. Okay, so we can say rank of A is 2. Okay, so that is how we find the rank. Okay, so these are all the concepts. Okay, one more thing was the Cramer's rule. Actually, we are not going to use it anywhere. It is just to find the solution of an invertible system. As of now, we already have so many ways to find the system, and also I will just mention that Cramer's rule. Okay, you can just refer the lectures if you want, or like anywhere you can just refer it for the details. I am not going to say about the Cramer's rule now. So let's go to the questions. So first question is, uh, what are all the possible values of determinant of an orthogonal matrix? Okay. First of all, do you know what is orthogonal matrix? Okay. A matrix A is orthogonal. A matrix A is square matrix only, orthogonal, if A into A transpose equals identity. Okay, if the matrix A satisfies the condition A into A transpose equal to identity, then we will say it is a orthogonal matrix. So just using this condition, can anyone say what are all the, just use the, what are all the result I have told in this class now? And can you say what are all the possible values of determinant of an orthogonal matrix? Any idea how to start?
Yeah, we can take a determinant on both sides.
Yeah, we can take the determinant on both sides. Determinant of A transpose equal to determinant of phi. So A transpose equal to identity means determinant should be equal. Now what we can do on the LHS?
The like separately we can apply determinant
Yeah,
to the product of
because
the two matrices.
yes, if we have two matrices A and B, determinant of AB equal to determinant of A into determinant of B. So A and A transpose is a multiplication. Okay. So determinant of A into determinant of A transpose. What is determinant of phi?
It's 1.
Yeah. Now what is the next step? What we can do from here? We
So
need to find determinant of,
determinant of
yeah.
A transpose is equal to determinant of A.
Yeah, determinant of A and determinant of A transpose are equal. So we already mentioned this result. So suppose determinant of A equal to, for simplicity we can write it is X. Okay, then determinant of A transpose should also be equal to X. So what we will get this equation star? X into X equal to 1, that is X square equal to 1. So what can be the values of X? X square equal to 1 means it has only two solutions, plus 1 or minus 1, correct? So
Yeah.
X can be plus or minus 1. So what is this determinant of A? For an orthogonal matrix, determinant can be either plus 1 or minus 1. Okay, now let us see. Okay, can anyone say some example of an orthogonal matrix with uh, determinant plus 1? You can start with a simple example. Just think about simple example. Okay, first I will give one example. Uh, take A equal to 1 0 0 1, like 2 by 2 identity matrix. Then what is A transpose? It is also identity matrix. Clearly A into A transpose equal to identity. So A is an orthogonal matrix. Okay, and determinant of A is 1. So we already proved it can be either 1 or plus 1 or minus 1. And we got an example with the determinant plus 1. Now we will confirm whether there exists an orthogonal matrix with the determinant minus 1. So if you are just modifying this example, you can find a matrix, an orthogonal matrix with the determinant minus 1 also. Can anyone say that? How we can write the matrix SEBI? Which matrix I can take such that it is orthogonal and its determinant is minus 1? Okay, first of all, it should be kind of determinant minus 1. So, no need to think about more complicated thing. Minus 1 means if we are taking these two 0, these two 1. So, obviously, it will have determinant minus 1 because 0 minus 1. Determinant of B is minus 1. And the B transpose is also 0, 1, 1, 0. Okay, determinant of B is minus 1. Now we need to check whether B is orthogonal or not. Okay, what is B into B transpose? 1, 0, 0, 1. Correct? So we got a orthogonal matrix B such that B into B transpose equal to identity and the determinant of B is minus 1. So whatever we proved, the determinant can be plus or minus 1. It actually attains also. Means plus 1 case also coming, minus 1 case also coming for some different matrices. Okay. Now next question. Let A be a 3 by 3 matrix with a non-zero determinant. If determinant of 2a equal to k into determinant of a, what is the value of k? This is a simple question. Anyone can answer this. So it is given k has a has non-zero determinant and determinant of 2a equal to k times determinant of a.
So if we multiply 2 with A, it will get multiplied to all the rows.
Yeah, 2a means it is multiplied with each element. That means
Each row.
every row. Yeah.
So we can take common from all the three rows,
Hmm.
right? So
The 2.
K will be 2 raised to 3.
Yeah, 2 raised to 3 because it is a 3 by 3 matrix and we have 3 rows. Okay. So, if one row is multiplied with one constant, while finding the determinant is multiplied. Like for example, if B is a matrix such that A, B, C, D, E, F, G, H, I, something like this. Okay. And my B dash is a matrix such that I am multiplying the first row with K, KA, KB, KC. Everything else is same. D, E, F, G, H, I. Okay. Still, I can take uh, this K outside. K times determinant of B. I mean, for matrix, I cannot write B dash equal to K times B. That is not true. But when coming to determinants, if one row is multiplied also, we can take that constant outside, then k into determinant of b. Now, what we are saying, a is multiplied with 2 means a is multiplied with each of the entries. That means with each of the row. Okay, from each of the row I am taking 2, 2, 2, 2, 3 times. So total 3 by 3 matrix. So 3 rows are there. So 3 times I am taking out the 2. So here determinant of 2a should be 2 into 2 into 2 into determinant of a. Okay, so that is 8 times determinant of a. So the value of k should be 8. So this is the nothing, just a property of the determinant. If one row is multiplied, the determinant is multiplied with the k times. Okay.
Ma'am, so if it is only determinant, not sorry, only matrix,
Hmm.
then and the matrix has k in all the rows, then if we want to take the common factor out of the all the rows, then
Hmm.
it is only k times the matrix, right? Once
Uh, uh, you are asking the matrix with the all entries k or multiplying all elements with k?
all elements are multiplied with k, 3
Ah.
by 3 matrix is multiplied by k,
Hmm.
so all the elements get multiplied by k.
Hmm.
So if we are given a matrix which is already having a common factor like k in the matrix, and if
Yeah.
we try to take a common out of the matrix, then it will be only one time.
Hmm.
But when we take a common out of the determinant, then it becomes raised to that many power of number of rows,
Yes.
right?
Yes. Yes. That only.
Then how can we understand it better? Like how does that happen? Like can we go into some little bit of mathematical like thing?
Okay.
Yeah.
Yeah, for example, what we have, we will start with the some, okay, 3 by 3 matrix we will start. A11, A12, A13, A21, A22, A23, A31, A32, A33.
And we can take
Okay,
a simple one also. It's okay. Like 2 by 2 is also.
yeah, 2 by 2 is also fine. Yeah, okay, then we will start with the 2 by 2. Okay, now I am writing first matrix as A dash equal to, I am just multiplying the first row only. K A12, A21, A22. So what exactly here happening is, uh, okay, I think 3 by 3 will be better for understanding, because here it is just one calculation. Okay, that cross multiplication only. So better it will be for A13, A23. Now, suppose our A dash is multiplying the first row with K. K A11, K A12, K A13. So, all the remaining are same. Now, while finding the determinant, by definition, what actually we are doing? We will start with the first element Ka11 and we will find the determinant of this portion. Okay, so Ka11 into some value. Okay, I am not writing the full term. In the next step, minus Ka12, we will take the second element Ka12 and determinant of the remaining portion. Okay, plus Ka13 into determinant of the remaining portion. So the remaining portion means we are considering with only the second and the third rows, means the submatrix from this second and third rows. Okay, but see here we have k in each of the terms. That k is actually going out. Okay,
Yeah.
that
Yeah.
k into a11 into the same value minus
Yeah.
a12 into same value plus a13 into the same value. So this is actually our determinant of a, right?
Yes. Yes. Yeah.
So that is why we are getting k
Per row.
into determinant of a.
Yeah, if it is all the three, then it will become k raised to
Yeah,
3.
because suppose in the second row also we have k. In this brackets also we will have one more k.
Yes,
That k
yes.
will also come outside. If
Yeah.
in the third row also there is a k, some k square will come, and along with the first k, total we have k cube. Correct?
Mm.
So that
Mm-hmm.
is what exactly happening when one row is multiplied with k, why this k is coming outside. Clear?
Indeterminate. Yeah.
Yeah, in case of determinant.
Yeah.
Okay. Uh, okay, now let's see the next question. Okay, if A and B are two n by n matrices, which of the following are true? Okay, so this is a very simple question. I already stated the result. And the second question is, okay, so what about the first option?
False.
No.
False. Yeah, this is false because we told A has rank n means A is invertible or determinant of A is non-zero. So clearly first one is false. What about second one?
False.
Second also false. Matrix multiplication is not commutative. And what about third one?
True.
It is true because
True.
determinant of AB, what is the
Oh,
reason? Determinant of AB we can split it as determinant of A into determinant of B. This is same as determinant of B into determinant of A, which is our determinant of BA.
yeah. But isn't this like a little bit counterintuitive to case 2? Because if we multiply them and then take a determinant, that will be different. But if we are taking determinant by applying rules, then it is same.
No, no. See what here saying is this is false actually. AB equal to
Yeah,
BA, that is
correct.
false.
Yes.
That means AB not equal to BA.
Yeah, but
But
my question is supposing AB is not equal to BA, and in case 3, if we don't take AB and BA, like we just say AB is equal to C1 and BA is equal to C2,
hmm,
C1, C2 are different.
yeah, different.
Now, in case 3, if you put C1, C2 instead of AB, BA,
Hmm.
then how their determinant becomes same?
Yeah, that only saying. Even though metrics are not saying, determinant
Okay,
is just a value. It can be same.
okay, okay,
Okay. In
okay.
general, what we can say, an example 0, 1, 0, 0 and 0, 1, 0, 0. Both are different metrics,
Okay.
but its determinant are same, right?
Mm-hmm.
Okay, that only. There is any
Got it.
confusion? Okay.
Yeah, yeah, got it. Thank you.
Yeah, now the next question is, let determinant of A equals 2 and determinant of B equal to 5. Suppose A, B are all same orders. Now question, find determinant of 2A square B inverse. How can we find determinant of 2A square B inverse?
Can determinant of uh, 2A square into determinant of B inverse.
Yeah, just we are using the non-result only, just multiplying like determinant of AB equal to determinant of BA. That result only we are using. And in the next stage, 2A square means, okay, let A be a matrix, suppose 2 by 2 matrix. Okay, here I need the order of the matrix, correct?
Yeah.
Suppose A is 2 by 2 matrix. Now, what is determinant of 2a square 4
Uh,
times, okay, a is 2 by 2 means a square is also 2 by 2.
okay.
Okay, so 2 times 2 has to come out 2 times. Okay, so
Yes.
4 times determinant of a square means determinant of a into determinant of a, that is determinant of a whole square into determinant of b inverse means 1 by determinant of b.
Why
Okay,
does it has to be 4? It has to be 2 only, right?
no, what is the order of a square? It is 2 by 2 matrix. Okay, 2 by 2 matrix means it has 2 rows. Okay, we are multiplying 2 with the full a square. That means we are multiplying 2 with each entry. That means we are multiplying with each of the row. Okay, as I told earlier, when we taking the determinant from first row, one 2 will come out, and from the second row again the 2 will come out.
Okay.
Okay, so 2 times 2, so 2 square, and determinant of a into determinant of a, and the determinant of b inverse is 1 by determinant of b. So total we will get 4 into determinant of a is given 4 and 1 by 5, so 16 by 5. Fine.
Yeah.
Okay. Okay, this I have already told. Uh, True or false. Okay, I already mentioned this, I think. If dit A equal to dit B, then A equal to B. Is that true?
No.
Okay. Oops. False. Okay, I have already mentioned one example also, so we will leave this now. Now next question. Which of the following are true for a matrix A? So statement 1, determinant of A plus A transpose equal to dit A plus dit A transpose if all entries are same, determinant of A equal to 0. Okay. Which one is true in this? Which one is false?
No, if all entries are same, the determinant of A is 0, because we had that rule that if any two rows are same,
Yeah.
determinant is 0. Um, but the first one,
Sorry.
there was no rule like that.
Okay. As of now, we don't know. Like under addition, we can separate this determinant. We don't know. Means it is not true in general. So if it is not true, we should give a counter example. Correct?
Yeah.
So, can you think about a 3 by 3 matrix such that this is not holding? The first case does not hold.
If we take identity matrix,
Yeah, definitely clear. So, we can always start with simple examples. Take A equal to identity. So, A transpose will also be identity. Okay. So, what is A plus A transpose? It is 2 times identity. Now, the LHS is determinant of A plus A transpose, that is determinant of 2i. What is determinant of 2i?
2 into 1.
Uh,
raised to 3.
yeah, because I we have given it is a 3 by 3 matrix. Again, as earlier I have mentioned, we have 3 rows means we have to take 2 3 times. Okay, so 2 cube into determinant of I, that is what we are getting. So it is equal to 8. Determinant of I is 1. Now, the RHS is determinant of A plus determinant of A transpose. That is determinant of phi plus determinant of phi. We know determinant of phi is 1. Okay. So this is 1 plus 1 equal to 2. Definitely both are different value. So the first statement is false. Okay. Any doubt? No. Let A equal to 2202. Find determinant of A power 10. Okay, again it is very easy question. What is determinant of A power 10?
So we can put determinant of A 10 times.
Yeah, determinant of A power 10 means A power 10 means multiplying A with A 10 times. So we can write it as determinant of A power 10. Okay. Determinant of AB equal to determinant of BA. If we have n multiplication, still we can split it like that. So that is what we are doing. So here what is determinant of A?
4.
4 power 10. Okay. So that is the value. So here one thing to note is if we have a diagonal matrix or triangular matrix, what will be the determinant? How can we quickly find the for a diagonal matrix or triangular matrix? I mean, not what will be the determinant. Means you can easily say in terms of some particular elements, particular entries.
Multiplication of all diagonal elements.
Yeah, just the multiplication of the diagonal entries. The determinant of A is the product of diagonal entries. Are you able to visualize it why it is coming just the diagonal entries, product of diagonal entries?
Yeah, because the last row will have only one entry and rest will be 0 in a triangular matrix.
Yeah.
So it will make everything else 0 except for that determinant.
Because for example, a diagonal matrix or triangular matrix, it will come like this. Here along the diagonal we have a non-zero entry, and if it is diagonal, here and here it is 0. Or if it is triangular, here it is some non-zero elements. For upper triangular it is 0 element. Now if we are taking the determinant, we will expand either along one row or one column. Suppose we are expanding along the row, sorry, column, first column. So corresponding to first element, we can find the determinant here. But corresponding to all the last element, like here everything is 0. So corresponding terms will go to 0. So in the same way, if we are considering the n minus 1 by n minus 1 case here also, corresponding to this only, the term will come. All other will go 0 because it is below the diagonal, everything is 0. So that is why intuitionally you can see why the determinant is the product of the diagonal entries. Okay. Okay, now let us see some problems in the adjoint of matrix. Which of the following matrices of order 3 are the same as their adjoint matrix? So question is, the matrix and the adjoint of that matrix are same. In which of the following cases it is true? Can anyone say in which of the following case it is true and in which it is not? What will be the adjoint of an identity matrix? Any idea? Okay, let us see a 3 by 3 identity matrix I 1 0 0 0 1 0 0 0 1. Okay, instead of seeing that we have one result, I think we can use that. We already know A into adjoint of A equal to determinant of A into I for any matrix. Okay, now if A equal to identity, okay, so what we will get the result? Identity into adjoint of identity equal to determinant of identity into I. So determinant of identity is 1. So this is equal to I. So what we are getting? Adjoint of I equals I. Okay. Is that clear? So we have this result here. This is what we are using. So this is a very important result while dealing with the adjoints. Is that clear for everyone? Or we can
Yeah.
Yeah, or we can like we already know how to find the adjoint, find the cofactor matrix. So in case of identity, it is very easy to find the minors, cofactors, and then adjoint and so on. So you can just verify also, find the minors, then cofactors, and then adjoint, and check whether it is identity or not. Definitely, it will come identity. Now, what about the zero matrix? Okay, now for zero matrix, if we are doing from this, we cannot say like here instead of if A equal to zero matrix we are giving, what we will get RHS is equal to 0, LHS is equal to 0. Like we are not getting anything about the adjoint, correct? So we can see if a matrix is 3 by 3 zero matrix. So what do you think what will be adjoint after seeing this?
Same.
Yeah, it should be 0 because in adjoint also what we are seeing like we will take one element, remove the corresponding row column and find the determinant of remaining. See, remaining also it is just zeros only. For example, corresponding to this 0, we will remove this and this. So what we will get? 0 into 0. Okay. So here corresponding to the first element a11, what we will get? Only 0, 0 only we will get. Okay, now corresponding to the second element also, second 0 also if we are taking, we will remove this and this, and the remaining is again 0. Like we have to multiply with minus 1 power I plus j and all, so we don't need to consider that because it is 0. So again, adjoint means it should come in the transpose way. If we are writing in row wise, we will get cofactor matrix. The transpose of cofactor is adjoint. So corresponding to this 0, we got 0 cofactor. So if I am writing it down here, 0, okay, then we will get the adjoint. So in the same way I can do for everything actually. 0 0 0 0 0 0 0. Okay, you can just do the calculation if you want, like from here only you can understand it will come 0 only. So adjoint A is also 0. Now we have two more
One
options.
question.
Yeah.
Uh, how do we get this formula A into adjoint of A is equal to determinant of A into I. Is this in something which we can like easily see, oh yeah, this is obvious, or is it something, some big derivation?
I don't think it is obvious. It is not
Okay.
obvious. I think it is covered in the class. Have you watched the lectures?
Yeah, I've heard. I think derivation is not there, but yeah, this statement is given that it is like this.
Yeah,
Okay.
derivation actually, as of now, I am not sure. Like, I can check if you want the next week. I
No,
can.
no, it's
Yeah.
okay. It's okay. I mean, I was just asking because this is something which, like, it's not.
No,
Uh,
I don't think it's so obvious.
okay.
It is
Hmm.
not so obvious, obviously. So,
Okay.
derivation will be there, but like some maybe some 2 3 steps only, but still we have to see that.
Okay. Yeah.
Okay.
Thank
Yeah.
you. Hmm.
Okay. Now we have two more matrices, scalar matrix. So, what is a scalar matrix? Scalar matrix means a
Const.
scalar, yeah, constant multiple of identity matrix.
Okay.
And what is diagonal matrix?
Like something like identity, but with a scalar.
No, that is scalar matrix. Diagonal matrix means all the diagonal entry can be different also. But in scalar matrix, all diagonal entries are same.
Okay.
Okay, it can be all diagonal entries are 2. It is a scalar matrix. Okay, but it is a diagonal matrix also. But for example, I have a matrix. Along the diagonal, I have 2, 3, 4, and all other entries are 0. Then it is a diagonal matrix, but it is not a scalar matrix. Okay, clear the
Yeah.
difference? Yeah. So all scalar matrices are diagonal, but all diagonal matrices are not scalar. Okay, now what about scalar matrix? What do you think? Will the adjoint be same or not? Identity itself is scalar matrix. Okay, for its adjoint is same as the identity. But in general, for a scalar matrix, will it be true or not? You can just start with some example other than identity. Just do like one or two operations like minus and cofactor of the first one or two elements, then you will be able to figure out. Take some 2 minutes and do it. Any idea? Any answer? Okay, let me give the. We will try with one example. So I am taking a scalar matrix 2 0 0 0 2 0 0 0 2. That means 2 times the identity matrix. Okay. Now let us see the minor corresponding to 2. What is the minor corresponding to 2? Here we will remove this row and this column. Okay. So we will find the determinant of this matrix. That is the minor corresponding to 2. So what is the determinant of this matrix? This is 4.
Oh,
Okay. Yeah. Minor corresponding to 2 is 4. Now, what is the cofactor corresponding to 2? It is just like minus 1. This is the 1/1th entry. So
Yeah.
minus 1 power 1 plus 1 into 4. Yeah. It is 4, right? Okay, so corresponding to first element we got 4. So if I am writing adjoint of A, so what is my first element? It is 4. Okay, do I need to go further now?
No.
No, because I got first element itself is not same as the previous case. Okay, for A first element is 2, for adjoint of A it is 4. So whatever it comes here, that does not matter. Adjoint of A not equals A. That is the only one question. Adjoint of A equals A or not. And we found that it is not equal. Okay, now from this can you say about diagonal matrix?
Same.
Same, because scalar matrix are all diagonal matrix. For scalar matrix it is not true. So obviously diagonal matrix also not true. The same example we can take that 202. So for this also not true. Okay, any doubt in this question? Okay then. Then we will go to the next problem. So which of the following are true? So everything is simple questions. Just give counter example or just using the non result we can figure it out. So first one is if A equal to A inverse, then determinant of A equal to 1. Okay. Can anyone give either the proof or the counter example? Statement is if A and A inverse are same, then determinant of A equal to 1.
Yeah, if A determinant of A is equal to 1 upon determinant of A inverse, sorry, A inverse is equal, determinant of A inverse is equal to 1 upon determinant of A.
Hmm.
So A square is equal, so determinant of A whole square is equal to 1.
Yeah, you are correct. Determinant of A inverse is 1 upon determinant of A. Okay.
Uh, so determinant of A is equal to 1. Okay. Uh, A
Uh,
square inverse.
what if I am giving a determinant of A equal to -1? Then again, this equation is again true, right? So what we are having is A into A inverse equal to identity.
Mhm.
So that is determinant of A into, okay, from here we cannot see anything. Okay, anyhow determinant of A inverse 1 by determinant of A. If determinant of A equal to 1, the star false. Correct. Okay.
Look, can we take determinant on both sides of the equation of A is equal to A inverse, right? So then it will be determinant of A is equal to determinant of A inverse.
A equal to A inverse, then
Then we take determinant
yeah,
on both the sides.
correct. Determinant of A equal to determinant of A inverse. So we can substitute in star.
Yeah,
Star implies determinant of A equal to 1 by determinant of A.
yeah.
Now what we will get?
So this will give determinant of A is equal to,
A square equal to 1.
mm,
Is that enough?
this is giving two values for
Yeah, two
determinant.
value possibilities there. Either
Mm.
determinant A can be 1 or determinant of A can be -1. So the question is determinant of A equal to 1. So if it is not equals 1, only one possibility is -1. So what we can think, if we are thinking about counter example, we can think a matrix A with the determinant -1. That is the only possibility. Okay. So think about such a matrix. If there exists a matrix A with the determinant -1 and A inverse are same. Just think like we have seen so many examples like just some arrangements of zeros and ones. That is all. Just try some examples where 0 and 1 are arranged accordingly. So that determinant is 1 and both A and A inverse are same. I have already gone through the example, like somewhere the same example. Anyhow, for identity, we cannot do anything because it has determinant 1. So, just some modification to identity will give a counter example actually. Okay. What about 0, 1, 1, 0? What is its determinant? What is the determinant of A?
1
Minus 1, right?
minus 1
Yeah, 0 minus 1. It is minus 1. What is A inverse? A inverse also 0, 1, 1, 0. You can just try A into A inverse is identity or not. Okay, A into A inverse is A inverse into A equal to identity. So this is our inverse. Okay. So what we got? A equal to, the condition given is if A equal to A inverse, then determinant of A is 1 or not. But we got A equal to A inverse. But our determinant is minus 1, not equal to 1. Okay. So we already found, using the given condition, we already found we have only two possibility, determinant of A is 1 or determinant of A is minus 1. But exactly, we have one matrix A with the determinant minus 1 and the A and A inverse are same. Okay, so we cannot say that statement is true. That is not true in general. For some matrix it is true. So the statement is false. So statement is false. Okay. Any doubt? Now we can see the converse. I am asking if determinant is 1, then A equal to A inverse. What about this statement? Now question is, the above question was A and A inverse are equal, then whether determinant is 1 or not. Now I am giving you determinant equal to 1, then whether A equal to A inverse or not. Again, I can say it is false. I just want you to give some counter example. Again, arrange. This is just an arrangement. Uh, like, see, here we have A and A inverse. You can see. Just, just modify this A. How can you modify this A such that its determinant is 1?
Yeah, if we take identity, it will be 1, right?
Then A equal to A inverse, correct? At that time. So my question is whether it is true or false. There we are getting a example for which it is true.
We can put 2 in A11, then uh, like 2, 2, 1, 1, 0.
A equal to
I,
2110. Okay, now what is determinant?
1, it is coming, but I haven't checked if.
No, determinant is minus 1, right?
No, 1.
minus 1 right
Oh, sorry, 2. Oh, yeah, yeah, sorry, it's 0. So 2, 1, 1, 1,
2, 1,
1, 1.
1, 1. Okay, so determinant of A equal to 1. Okay. Now only thing is A equal to A inverse or not. Okay. So instead of finding A inverse, we can check if A equal to A inverse A into A inverse equal to identity. Okay, no need to go to finding A inverse, but we know that A inverse is A, that is A square should be equal to identity. So we will see what is A square. A square equal to for 5. Okay, it is not identity. So that is one example, perfect example. So okay, you can see or what are all the other elements. So first entry itself is 5. Okay, is that clear?
Yes, yeah.
Yeah. So this is not going to be identity. So the statement is false. Okay, what I was going to do with this example is, here itself you can just modify, instead of this 1, if you are taking minus 1 here, then determinant is minus, like plus 1, right? So that is what I was trying to tell. Okay, that is fine, you can just try with it.
Okay. Yeah.
Okay, try with A equal to 0 minus 1 1 0. So the positive thing of this kind of thing is, to find the inverse it is easy. Okay, otherwise, like in the earlier example, the thing is, okay, we can use like this, but still to find the inverse it is a bit difficult, we need to find the adjoint and all. So for this example, just by inspection we can find the inverse. Okay, okay, anyhow, you can just try that. Now the next statement is, then A is identity. Okay. Can anyone say what about whether it is true or false? A is given equal to A inverse, then A is identity. You can just say from the previous examples itself. What we got, A equal to A inverse in the false. Yeah, in the first example, what we got, if A equal to A inverse, determinant A can be plus 1 or minus 1, and we
Yeah.
found an example with the minus 1. So in that case, A is not identity, obviously. So what was that example? A equal to 0 1 1 0. That is same as A inverse, but A is not identity. So it is a false statement. Okay. Now the question, there exists for any n in n, there exists a n by n matrix such that A equal to A inverse equal to adjoint of A. What about this statement? That is, for any order n, we are claiming there exists a matrix A such that it is same as its inverse and its adjoint. Can you think about any such matrix? Yeah, identity matrix. We have already seen for identity matrix, the adjoint is same identity only. Also, A inverse also we already know for identity matrix. Yes, true. Take A equal to identity. Okay, that's all. Okay, next is, if A inverse equal to adjoint of A, then determinant of A equal to 1. Okay, again, yeah, true. Okay, someone has answered it is true. Can anyone give explanation for that? Yeah, by definition. Yeah, we already know that A inverse equal to adjoint of A by determinant of A. Okay, this is the definition of A. Okay, from this we already what we are saying, A inverse and adjoint of A are same. So only possibility is determinant of A should be equals 1. Clear? Okay, now let us see one question. To find the rank, find the rank of the following matrices using determinants. So I will write the matrix. So in between you can try to find the rank of the matrix. Just use the definition of determinants instead of like reducing it to row echelon form. You can try start with the first one, A. Anyone check the A?
Yeah, it's full rank, I think.
Full rank. Yeah, A has rank 3 because if we are finding the determinant of the first matrix, then determinant will be non-zero. So you can calculate the determinant. A has determinant non-zero, so rank equal to 3. Now what about the B matrix? First find the determinant of B.
I think this is also full rank.
Are you sure?
Not like I just tried two elements and they look positive. So, but I can try again.
Yeah, rank is 2 actually. Okay, calculation, yeah, you just redo it. Otherwise, like I can, okay, actually we need to find the determinant, that is the way. Otherwise, you can, by inspection, you can say, you can see the third row is actually the sum of the first two rows. 2 plus 1 is 3, 1 plus 2 is 3, 3 plus 5 is 8. So, rank should be less than 2, less than or equal to 2. Okay. Okay, find the determinant of B. Determinant will be 0. Okay, determinant will be 0, and we can take any submatrix. For example, we can take 2 1 1 2. So its determinant is non-zero, its determinant is 3. Okay, so it is non-zero, so rank will be equal to 2. Now what about option C? Yeah, option C, rank is 1 because the second row is same as the first row. Okay, obviously the determinant is 0. Okay, now the option like rank 2 is not possible because it is a 2 by 2 matrix with the 0 determinant. Now we will go to the square matrix, sub-square matrix of order 1. So we can take the matrix here determinant equal to 0, but determinant of the submatrix 1 of order 1, that is the first element 1 itself I am taking. Okay, it is non-zero, so rank equal to 1. Now what about the option D? Option D, rank 3, no. Sorry. Okay, sorry, 1 minute. 3, 6, 9. Okay, there is a small change in the option D. The last entry is 9. Still, is that rank 2?
It's one.
It is 1 actually, because the second row and the third row, yeah, sum of two rows is third. So third row we can omit it without any problem. But see, the second row is actually the multiple of first row. Likewise, third row is also a multiple of the first row. Okay, yeah. But if it is like, if we are finding the determinant, first we need to find determinant of the given matrix. It is 0. Now find determinant of all 2 by 2 matrix. Actually, we should find all the 2 by 2 submatrix. For example, we should take this matrix 1 2 2 4, and then 2 4 3 6, and also we are supposed to take 1 3 3 9. This is also a kind of submatrix. So all those kind of submatrix, and we should verify that it has determinant 0. Okay, find determinant of all 2 by 2 subsquare matrix. They are 0. Okay, then only we should go to the third level, that is matrix of order 1. So rank equal to 1. Okay, now the last question, what about the option E? Again, it is very easy. Yeah, rank is 1. Like 3 by 3 matrix, it is not possible. Maximum possible submatrix is 2 by 2. For 2 by 2, if we are considering any possibility, the determinant is 0. So rank is 1 only. 1. Okay, now next question is, if sum of all entries of each row of a matrix A is K. Okay, let us take the square matrix here. Square matrix A is K. Then which of the following are true? If K equal to 0, A is not invertible. What is not invertible means? Not invertible means determinant is 0. And the second option is, if K not equal to 0, A is invertible. Okay. So the question is, we have a square matrix A. What I am saying is, I am taking one row and adding all elements in the row. So I got an element K. Suppose K equal to 0. That is, sum of all entries equal to 0. In every row is 0. Now question is whether A is invertible or not. So the statement is A is not invertible. That is, A is not invertible means determinant of A equal to 0. Okay. Any guess on the first question? Yeah. First one is true. Can anyone tell the reason why it is true? The sum of rows is 0, then A is not invertible. Okay, let me explain that. It is not So you see, first thing, if I am taking a matrix, uh, okay, so option A, okay, we are taking the system Ax equal to 0. Okay, we already seen the linear system Ax equal to 0. First of all, x equal to 0 is a solution. Okay, can anyone think about a solution of this given system Ax equal to 0 other than this trivial solution? It is a trivial solution. Okay, from the given condition, what is the given condition? Sum of the rows, entries of row equal to 0. Okay, so using that, yeah,
Yeah, determinant of A is 0, then also this equation will be satisfied, right?
uh, yeah, if determinant of A equal to 0, it will be satisfied. Like, but can you conclude that it is determinant is 0 always? The question is whether determinant is 0 or not. If determinant of 0 is 0, okay, x equal to 0 is a solution, but there is a non-zero solution also. Correct? If A is invertible, then we have only one solution. Our question is uh, whether A is invertible or not. The given condition is the sum of the rows is 0. Okay, let me explain that. Given condition is sum of the rows equal to 0. I am taking the linear system Ax equal to 0. Okay, now I claim that the 1 1, suppose A is an n by n matrix, etc. 1. This is an n by 1. Is a solution of Ax equal to 0. Is this true? Whatever I have written, is this true? Or are you able to see it as a solution of Ax equal to 0? Why I am claiming that it is a solution? What is A into 1 1 etc. 1?
Yeah, anything which is multiplied with 0 would be because we have a trivial solution x, right?
Yeah, trivial solution is there.
Yeah.
Trivial solution is there. So from that, are you able to conclude anything? Sum of element of, okay, yeah. Are you able to conclude anything? See, I am saying this 1 1 1 is a solution. Okay, yeah. Yeah, I am saying this 1 1 1 is a solution. Okay, because if I am taking A into 1 1 1, what I will get? Sum of first row. So this is an n by 1. Okay, what I am taking? The first row I am multiplying with this given 1 1 1. So that is the sum of first row. Next is sum of second row, etc. Sum of nth row. Okay, we are given that all these sums are 0, 0, etc. 0, n by 1. Okay, so I can say 1 1 1 1 is a solution of A. Other than the trivial solution 0, I got a non-trivial solution 1 1 1 1. Okay, now can A be invertible now? If A is invertible, what is our result? Rank of A equal to n. Okay, rank A equal to n, which is equal to number of columns of A. In this condition, we have only trivial solution. Okay, but what we got? It has a non-trivial solution. 111 is a, but ax equal to 0 has a non-trivial solution. So its rank cannot be equal to n, right? Rank is strictly less than n. Yeah, rank is strictly, yeah, actually infinite solutions are possible. Either we have like unique solution or infinite solution. Finite solutions are not there. So what we got? Rank is strictly less than n. If rank equal to n, it is invertible. If rank is strictly less than n, it is non-invertible. That implies A is not invertible. Okay, that means dit A equal to 0. That is our question, whether A is invertible or not invertible. Okay, is that clear for Swati?
Not very clear actually. I'm trying to understand completely.
Okay, okay, I will explain once again. So, what we are doing is, given that sum of the rows, like sum of the entries in the rows equal to 0. From that, using that, we are trying to find one solution which is a non-trivial solution. Okay, we are taking the system Ax equal to 0. For Ax equal to 0, we are claiming that the column 1, 1, 1, etc. 1 is a solution. Okay, for that we are taking A into column 1, 1, 1, 1. Okay, that is what we are doing in the first one. So A into 1, 1, 1 means what we will do? Multiply the first row of A with the column 1, 1, 1. So what we will get? Sum of first row. That is 0. The same way we will get each row equal to 0. So we
Yeah,
got a non-trivial solution for the system Ax equal to 0.
correct.
Non-trivial solution is there means rank cannot be full rank. If full rank is there, only trivial solution, that we already know. Correct? So,
Okay.
uh, if we are getting it is not full rank, it is not full rank means it is not invertible. Okay, that is how we are concluding A is not invertible.
Sorry, how did, sorry, so now we got a solution 111, which is, so all the values of the variable matrix are 1, right? So we got a solution which is unique.
No, no, here solution is not unique, right? Like we already have the trivial solution. Other than
Mm.
that, we go to one more solution.
Okay.
So it is not unique, right?
Okay, so we got two solutions, and
Yeah.
that is why, uh, and that is why A is not full rank, and so it is not invert. So that is why the determinant is 0.
Yeah. See, suppose if A is full rank, that means rank A equal to n, then A is invertible.
Okay.
Okay. So what
Yeah.
we are having, if uh, A is invertible, what we can say, rank A
Determinant
equal to
not
n.
is
Okay,
okay.
determinant is okay. From here, rank A equal to n.
Yeah.
And Ax equal to 0, that implies, yeah, that is what he is saying. A inverse Ax equal to 0 implies x equal to 0. That
Hmm.
means x equal to 0 is the only solution. Like
Yeah.
whatever the solution we are starting with, if we are multiplying A inverse, pre-multiplying A inverse, we will get x is 0. There is no other
Hmm.
solution other than 0. But that
Yeah.
is not true in our case. We got a solution 1, 1, 1, etc.
We
1.
got more.
Okay, that is why we are saying A is not invertible. If A is
Okay.
invertible, it should be satisfied here. It is not
Yeah.
satisfied.
We
Okay,
got more than one.
yeah, we
That's why.
got more solution.
Mhm.
So A should
Yeah.
not be
Got it.
invertible. That's all.
Mhm.
Okay.
Thank you. Yeah.
Now the next question is again sum of the entries. We are taking a non-zero value. Now question is A is invertible or not. You can try with examples also, like try with some one or two examples, like for invertible matrix it is true, or for non-invertible matrix it is true. That means sum of entries are same. Okay, whether A is invertible or non-invertible. Okay, let us start with the identity matrix. Does this satisfies the given condition? What is that is sum of entries are equal, non-zero value? Yeah, sum of row entries equal to 1 and A invertible. Okay, but can I conclude it for general? Like I have given one example, it is invertible. Can you find the other examples with the sum of entries are non-zero, but it is not invertible? Can you think about such an example? Anyone? Just take any matrix, not invertible, but the sum of entries equals to a non-zero value, like row entries. Okay, I will give you the example 1 0 0 1 0 0 1 0 0. What about this? Does it satisfies the given? Yes. Yeah, someone has given another example. Some matrix are equal to 1 2 2 2 2 2 2. So sum of row entries. Here sum of row entries is 4, not invertible. Here also sum of row entries. For each row, sum of row entries is 1. Again, not invertible. You can easily see why it is not invertible. So, if it is a 0 value, we have a like result. It is not invertible. But if it is a non-zero value, sum is a non-zero value, then it can be invertible. Yeah, it can be invertible or it need not be invertible. So in general the statement is false. This is first one is true and this statement is false because there is no general thing, like we cannot say it is invertible. Okay, good. Okay, now the next question is, if a square minus 2a minus I equal to 0, find a inverse in terms of a. This is just an algebraic calculation. Can anyone say what is A inverse? Write it in terms of A identity matrix and all. Like not the exact value I am saying because we don't know what is A. How can we simplify? Yeah, A minus 2A. This is very simple. Like A square minus 2A equal to identity. Okay. If we are taking A outside, what we will get? A minus 2A equal to identity. The inverse is unique. If we are getting some matrix such that matrix into A equal to identity, then this should be equal to A inverse. So, A inverse equal to A minus 2I. Okay. Now one similar question. Let A, given A is an invertible matrix, and it satisfies the equation 3a cube plus 2a square plus 5a plus I equal to 0. Now, can you say what is A inverse? It is just like the earlier one. How can you say, like, what is the expression for A inverse? Okay, as earlier, either you can keep the I this side and take all the, okay, yeah, I this side and take all the elements the other side, minus 3a cube plus 2a square plus 5a. From this we can take a outside, or directly you can multiply, yeah, I minus 3a square minus 2a. So directly you can multiply the star with the A inverse, that is also possible. Okay, from this what you can do, take the A outside, so 3a square plus 2a plus 5a into A. Okay, so this is the, this including this minus, okay, this is our A inverse. Okay, okay, now we will do the, okay, question, if determinant of A equal to 0, okay, again true or false, if A n by n matrix and determinant of A equal to 0, then determinant of adjoint of A equal to 0. Okay, so question is, if A is given with the determinant is 0, then what about determinant of adjoint of A, whether it is 0 or not? Okay, I will, you can use, yeah,
This is true because of the equation of
because of the which
A
identity, A
adjoint
into,
of A is equal to determinant of A into I.
yeah, how can you conclude from this?
Here determinant of A is 0.
Hmm.
So 0 into I matrix will be 0, and so A into adjoint of A is equal to 0.
A into adjoint of A equal to 0 matrix, correct?
Yeah.
0 matrix. Okay, then
We can multiply by A inverse and make it on both the sides, and
no, determinant
it
of
will
A is
become,
0, so A inverse does not exist.
yeah.
So what we can do?
We wanted to prove that determinant of A is 0, right? But A itself is not 0, so determinant of A has to be 0.
Sorry, can you repeat? If A itself is?
So A itself is a matrix which is not 0. If we take a determinant uh, of this, then we get determinant of A into determinant of adjoint of A,
Hmm.
uh, where um, but determinant of A is 0. So, but we that doesn't prove that adjoint determinant of adjoint is also 0.
Yeah, that doesn't prove. So let us prove by some contradiction method. So what we want to check is determinant of A is 0 or not. Sorry, determinant of adjoint A is 0 or not. Okay, suppose, okay, for simplicity let B equal to, let B equal to adjoint of A. Suppose determinant of B equal to determinant of adjoint of A is non-zero. Okay, now what we are having is A into adjoint of A equal to determinant of A into identity. Okay, for adjoint of A we have notated it as B, that is determinant of A into identity. Now since determinant of B, that is determinant of adjoint A is non-zero, it is invertible and the inverse exists. Okay, so what we will get, uh, AB B inverse equal to determinant of A into B inverse.
Actually, we have taken the equation A adjoint of A,
Hmm.
but we have not taken determinant yet, and we have replaced adjoint with B.
Yeah.
Okay. B is adjoint of A. Okay, sorry.
Hmm. Sorry, 1 minute. Okay, so AB inverse equal to, so what we can say is A equal to, uh, which is equal to 0. There is some confusion actually. I'm sorry. Okay, just give me 1 minute. Okay. Yeah, sorry, I was having some confusion there. Okay, what we are getting is A equal to 0. Okay. Now, what is adjoint? Okay, is this clear till now?
Yeah.
Yeah. Now, what is adjoint of A? A is a zero matrix, correct? We already proved for a zero matrix. What is the adjoint? Zero matrix, right? For identity and zero, the adjoint are same as the, like for a zero matrix, the adjoint is zero matrix. Similarly, for identity matrix, the adjoint is identity. Okay, so adjoint is 0. Okay, now what is determinant of adjoint of A? 0. Now we got a contradiction, correct? We were having we started with the determinant of adjoint of A is non-zero, but after doing some calculation we got determinant of adjoint of A equal to 0. That means we got a contradiction. This is a contradiction. Why the contradiction occurs? We assumed the determinant of B is non-zero. Actually, determinant of B should be equal to 0. Like this multiplying with the B inverse is not possible actually. That is the reason why we are getting the contradiction. Okay, that implies determinant of B should be equal to 0. That means the determinant of B is our adjoint of A should be equal to 0. Is that fine? Sorry, in between I was also having some confusion. It is just an arrangement and like we are reaching to a contradiction. Yeah.
Can you please explain once? Not very clear.
Okay. So we are just starting with the identity A into adjoint of A equals to determinant of A into identity. Okay. Our question was, if determinant of A equal to 0, then determinant of adjoint of A is 0 or not. We are assuming it is not 0. Okay. We assumed the determinant of adjoint A is non-zero. Since it is non-zero, adjoint A is a matrix with a non-zero determinant, means it is invertible. So, to this equation, we are multiplying with the inverse of the adjoint. For simplicity, we have taken B equal to adjoint of A. So, we are multiplying with the B inverse, that is adjoint of A inverse in this step. Okay. From that, B into B inverse is identity. So, we will get A equal to 0 matrix. Okay. For a 0 matrix, adjoint of the 0 matrix is also
Actually,
0.
how did the zero come? Like A is equal to determinant of A into B inverse.
Yeah, because determinant of A is given to be 0, right? In the
Okay, okay.
question. Okay.
Mm-hmm.
So the
Mm-hmm.
right hand side will become 0. 0 means
Oh,
it is a 0 matrix. 0 into a matrix.
yes,
Okay.
yes.
So A is a 0 matrix. So adjoint of A is also a 0 matrix.
Okay.
Okay. So adjoint of A is 0 matrix means determinant should be 0. For a 0 matrix, its determinant is 0, correct? But it is a contradiction because we started with the determinant is non-zero from the beginning. But we are getting determinant is 0. So this is a contradiction. So we can say determinant of adjoint of A should be equal to 0.
Okay.
Fine?
Yeah.
Okay. Uh, okay. So I think. Okay, maybe one more question I will do quickly. Again, question is true or false. If determinant of adjoint of A equal to 0, then determinant of A equal to 0. The same way we can do, suppose det not equal to 0. Okay, that means determinant of A equal to 0. That is what? Determinant of A equal to 0. When determinant of A equal to 0, how can we assume determinant of adjoint? Can you specify where did we assume determinant of A equal to 0? Yeah, can you please unmute and talk? I am not clear about your doubt. I mean, I didn't get it. Okay, okay. Did, did I use determinant of A equal to 0?
Ma'am, you can put line numbers and then he can put which line he's
Yeah,
telling.
yeah, okay, fine. 1, 2, 3. I think just after this. 7, 8. Okay, which step you are mentioning? In which step we are using determinant of a equal to 0? Ma'am, in the question we have determinant of a equal to 0. Yeah. Yeah, the question is if determinant of a equal to 0, whether determinant of adjoint of a equal to 0 or not. Okay, that is the question. So we have proved it is true. As of now, we know determinant of a equal to 0 implies determinant of adjoint of a equal to 0. We were not knowing that. Now we proved it. Okay? Yeah. So, like that is the proof is given as the answer. Okay? Now the yeah we will just quickly go through this also. Again we will start with the a into adjoint of a. It's correct, right? Okay. Determinant of a into identity. If again the same way, if determinant of a is non-zero, I can multiply with the a inverse. Okay. So a inverse a into adjoint of a equal to determinant of a, sorry, not the same procedure. Let us take the determinant on both sides. Okay, what we will get is determinant of a into determinant of adjoint of a equals determinant of a power n. Suppose a is an n by n matrix. Okay, a into adjoint of a is determinant of a into I. So I am taking the determinant on both sides. Now, if determinant of a is non-zero, what can you conclude from that? Okay, from this what is determinant of adjoint of a?
Determinant of a raised to n minus 1.
Determinant of a power n minus 1. Okay, this we can do because determinant of a is non-zero. If it is 0, we cannot like do the division. Okay, since it is non-zero, we can write like this. Now what is this?
Given that determinant of adjoint of a is 0, so we have to prove that determinant of a is also 0. So we can replace determinant of adjoint of a as 0, then
Yeah, this is 0.
determinant,
But what is this? This is non-zero, right? Like what we are assuming determinant of a is non-zero.
yeah,
So we got a contradiction again. Like from the given condition, determinant of adjoint of a is 0. That is this side. But since we assumed if determinant of a is not 0, we are getting it is not 0. So we are reaching to a contradiction, correct?
yeah,
So why the contradiction? The assumption here is wrong. It is 0. So the statement is again true. Okay. So determinant of a should be equal to 0. Is that fine?
yeah. Determinant
Okay.
of this statement is true.
Yeah, statement is true.
The last one was false, right?
The last statement, yeah, that is false. Like that is actually not false, that is a contradiction. Like we are starting with something, so we are reaching some contradiction, means wherever we started, that assumption is wrong. Okay, that is why we use the contradiction method.
Correct.
Okay, so we started with the determinant of a non-zero and we are reaching a wrong statement, a contradictory statement. So the first assumption, determinant of a non-zero is false. That is determinant of a is 0.
0. So that is also true then. Okay.
Yeah, the statement, given statement is true.
Okay. Thank you.
Okay. Okay, repeat the statement. Okay. So the question is, if determinant of adjoint of A is 0, then determinant of A is 0. Uh, I am trying to prove this. For that, I am assuming this is non-zero. So determinant of A is non-zero, I am assuming. Now I am using this identity A into adjoint of A equal to determinant of A into identity. So taking the determinant on both sides, since determinant of A is non-zero, because I assumed that determinant of A non-zero, I can divide with the determinant of A on both sides of this equation. Correct? Then I will get determinant of adjoint of A equal to determinant of A power n minus 1. But determinant of A is non-zero by assumption, so it is not equal to 0. And by the given condition in the question, determinant of adjoint A is 0. So what we are getting is one value, that is determinant of adjoint of A, which is equal to determinant of A power n minus 1. It is 0 and it is non-zero. Okay, that is a contradiction. We are starting with a statement, we are reaching at a contradiction. Okay, why we are reaching contradiction? We are starting with the wrong statement. So our starting statement is wrong. So the, like, since starting statement is wrong, we should modify it. Determinant of a non-zero is wrong. So determinant of a 0 is the correct answer. Is that fine for you? Okay. So anyone has any other doubt?
There was a question related to symmetric and skew symmetric matrices
Yeah.
in the assignment.
Yes.
So that had little bit like determinant when n is odd and determinant when n is even. So there were questions like that for skew symmetric and symmetric matrices. So, like if it is a skew symmetric, then when n is odd, then determinant is 0. But if n is even, then determinant of the skew symmetric is a square of a perfect square or something like that. There were, is that true? I couldn't
Oh,
prove.
yeah, I cannot answer actually, but what I will suggest you to start with like SQ symmetric matrix, 1 by 1 skew symmetric, 2 by 2 skew symmetric, like different
Okay.
odd even, like how the form will be for a skew symmetric matrix. Like skew symmetric means A transpose is minus A, like that, right? So
Yeah.
start with some general matrix. Okay,
Okay.
like A11, A12, like that, start with the general matrix. Just try what actually the determinant comes.
Okay.
Okay, from that you will get some idea how it will come. Okay,
Okay.
you just start with,
Is it true
yeah.
that for skew symmetric diagonal always have to be 0?
Yeah, for skew symmetric A transpose equal to minus A, right?
Yes. Yeah. So does
Yeah,
that,
the diagonal should be 0, correct?
okay.
Because for example, suppose it is a non-zero entry in the diagonal. This is our A, like we don't know what is the remaining element. I'm taking first element, a diagonal element. Now
Because
A
ma'am,
transpose
because,
also have
if
2.
we just say A transpose is equal to minus A, then transpose will, even if it is non-zero, it will work, right? Just elements are negative. Other elements, non-diagonal elements are opposite sign.
Huh?
If we transpose, it will still be A transpose is equal to minus A. So diagonal don't necessarily have to be zero based on this given condition alone.
No, wait. See, if I am taking an element, like non-zero element here,
A simple, okay.
okay, this is my matrix A. First element is 2. That is a diagonal element. Let
Hmm.
us see. All the remaining, we don't know, whatever it is.
Okay.
And like in A transpose also, first element will be 2 only. Like I am taking transpose.
Yes.
A equal to minus A transpose. Okay.
Yeah. Yeah.
But here minus A transpose equal to some minus 2 and whatever the negative elements here. If A and A transpose are equal, both should be 2 minus 2, like
Okay.
positive negative part should be equal, right? So it should be
Okay, I
0,
got
right?
it. Yeah, yeah.
Yeah, so it should be 0 actually.
Okay.
Yeah.
Yes.
Okay. Any other doubt? Okay, so I think let's stop for today. Okay, thank you everyone. We will meet in the next week again. Okay,
Thank you.
bye for today. Yeah,
Good night.
yeah, good night.